Welcome everyone. So today we have a very special problem. Like these type of problems, if you are able to tackle in the exam hall, then it would be really great. So there are no particular way to tackle this problem unless and until you kind of sit down and uh, let's say work it out yourself. All right. So the key factor here we need is what are compact spaces of Rn. So by Heine-Borel theorem, we know that the compact spaces or compact subsets of Rn are those subsets which are both closed and bounded. All right. So one of the things that you should uh, take note here is that since we are talking about M3R as R9, then you should understand that what should be its norm, right? The metric. Because, like, if you want to prove a certain set is closed and bounded in an Euclidean space, then you need to sort of define the metric over that space. You need to define a metric over that space, right? So, generally, if I have a metric A in M and R, so then the Euclidean metric of that or the Euclidean norm of that metric is nothing but root over just a second. Uh, so root over summation of I equals to 1 to n summation j equals to 1 to n aij whole square. Now it is pretty evident that why this is so, because you are actually taking A as the tuples aij. Okay, because see, the moment M in R is getting identified with R n square, that is that exact same moment you are considering your matrices as nothing but n square tuples. So what is suppose you have a1 till an square. If you have this tuple, then what is the Euclidean distance from here to 0 comma 0 comma 0? So that's precisely root over of e1 square dot 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 plus an square, right? So that is precisely this element. Okay, so that is the reason that we have this norm. So what our goal is in this problem, first our goal is to prove that uh, so suppose if let's see what was the set. Yeah, so if A is the set, so if A is compact, let's take this some A tilde, this is matrix, so we will, yeah, so if A is compact in R9, then A has to be closed and bounded. So one of the way you can actually prove, or if the subset of Rn is bounded, that means what? That means if I pick any matrix, let's just say if I pick any matrix X in A, then norm of X over E, it has to be bounded. All right, because otherwise the distance, if the distance is not bounded, by so what do we say, that when does a subset of an Euclidean space becomes bounded? When is a subset of an Euclidean space is bounded? The subset of an Euclidean space is bounded if and only if it can be put inside a closed disk. So suppose you have this as R2. Now this is something that is bounded. Why? Because you can actually put it inside a closed disk. So that is the exact same reasoning that you need to prove boundedness in Rn. That means you are actually putting it inside an n-dimensional ball. All right. So now suppose let X be the matrix this. So if you take the characteristic polynomial of X, you will see that that polynomial is precisely what is given, plus 2x minus 1. Now, how did I come up with this matrix? So the way I come up with this matrix are pretty simple. Since it is a 3 cross 3 matrix, so as you can see that the problem suggests that A is a subset of M3R 3 cross 3 with characteristic polynomial this. So how does the characteristic polynomial is defined? So the characteristic polynomial, so this part is the trace part, right? So this is the trace part. This has to be the determinant part, and this is the linear combination of the roots, right? So that is the exact same way I actually constructed it, very basics. So this is something that you need to put in a little bit of work. So see, how do we get to trace 3? So the basic way to put trace 3 is in this way, right? And we are also using I mean in the background the Cayley-Hamilton theorems. All right. So if you want 3, then just put it 0, 0, 3, right? That is the best way you can get it. Now if you want the determinant 1, then how can you adjust the other sides, provided these 3 things are fixed? And then if you want 2, then what should be the adjustments finally? So if you take this, then if you take the characteristic polynomial of this matrix, you will always get this I mean this polynomial. All right. Now the problem is that, okay, so that means what? This X is in A, right? Now if A was compact, that means the norm of X, the Euclidean norm of X, it has to be bounded for all n. So that is the last step. So if A was bounded, if A was compact in R9, which implies closed plus bounded, had to be bounded for all n, because it cannot be unbounded, because the moment norm of a matrix becomes unbounded, that means there does not exist a single n-dimensional or 3-dimensional spheroid or disk that contains all the points. Okay, so that is the visualization that we have also discussed here. Okay, so this, always remember that boundedness in Rn means you are actually putting it inside a closed disk. So it starts from linear cases. I mean, when do you say a set is bounded? I mean, like an interval is bounded only when you can actually put it inside a closed interval, right? Only then you can actually say that it is bounded. So now closed interval in 1 dimension, closed disk in 2 dimension, closed spheroid in 3 dimension, so on and so forth. So it has to be bounded. But if you compute with the provided matrix, the matrix that I have actually listed down here, if you compute norm of x over E, so this will look like something like this. So I'm just avoiding some very basic level computation. Okay, so this is the computation that you will get. All right. So the moment you get this as the Euclidean norm, what you have is that this Euclidean norm, it is always greater than 3. It is strictly greater than 3 and it is unbounded. This norm is unbounded. If n tends to infinity, the norm of x over E is unbounded. All right. So that means what? If n tends to infinity, this part that will go to 0, but this part will shoot towards infinity, and this is something that you have 3 always. So the norm itself becomes unbounded. So the moment it becomes unbounded, it is a contradiction that E is compact. It's as simple as that. Okay. All right. So for joining, we will meet with another problem in the upcoming session.